Good morning, students. So today we are going to discuss about 17th group. We will discuss various physical and chemical properties of 17th group elements. These group elements are also known as halogens. So we are going to discuss about various chemical, physical properties of halogens, and then we will discuss about important compounds of this family. Okay. Now let us start with group 17 elements. So this group is also known as halogen family, and the different elements in this are fluorine, chlorine, bromine, iodine and astatine. Okay, now since it is 17th group and it is in the p block, so its valence shell electronic configuration is ns2np5. Okay, now fluorine and chlorine, they are fairly abundant, while bromine and iodine are less. Means we are talking about where they occur. So fluorine and chlorine, they are found easily, but bromine and iodine, they are less found in nature. Okay, fluorine is present mainly as insoluble fluorides, fluorspar, cryolite, fluoroapatite. Okay, in this type of minerals it is present. Now small quantities are present in soil, river water, plants, bones and teeth of animals. There is little amount of halogens. Okay, seawater also contains chlorides, bromides and iodides of sodium, potassium, magnesium, calcium. Okay, but there is mainly sodium chloride in seawater. So means what we say seawater is salty in nature, so it means there is presence of sodium chloride in more amount, but other salts are also present like chlorides, bromides or iodides. Okay, now if we talk about electronic configuration, then they are having atomic numbers 9, 17, 35, 53 and 85. If we see their valence shell electronic configuration, then we will find that there is ns2np5 electronic configuration. They all are of 17 group, and when we start moving from top to bottom, then there is increase in the main energy level, and that main energy level is called period number. Okay, now to start with chemical properties, first of all let us discuss oxidation state. Now see, if we talk about fluorine, then its oxidation state will be 1 only. Okay, that is -1. But if we move ahead, then there is presence of +1, +3, +5, +7 oxidation states. Why is it so? Because for fluorine there is absence of vacant d orbital. So its valence electrons cannot jump to higher orbital because there is no more orbital present. But except fluorine, for all other elements there is presence of vacant d orbital. So electrons can jump to higher orbits. Okay, so whenever this thing happens, then number of unpaired electrons increases. In the ground state there is presence of only one unpaired electron, so there may be this oxidation state value may be -1 or +1. But when there is first excited state or second excited state or third excited state, then the number of unpaired electrons that increases, and because of this what happens, there is increase in the number of unpaired electrons, and so this increases. Now see, here there is some mistake, it should not be there. There is only one unpaired electron. So one unpaired electron, three unpaired electrons and three more unpaired electrons. So there are 7 unpaired electrons. Okay, here there are 3 unpaired electrons. So let us see again. In the ground state there is only one unpaired electron, so -1 and +1 is the oxidation state. In the first excited state there are 3, so +3 will be the oxidation state. Now when this electron again jumps ahead, then there are 5 unpaired electrons, and when this also jumps ahead, so here will be only one unpaired electron, and total will be 7 unpaired electrons. So because of 7 unpaired electrons, there will be +7 oxidation state. Okay, so now when we talk about reactivity, then out of all halogens, this fluorine has maximum tendency to accept an electron, so it is the strongest oxidizing agent. Okay, what is oxidizing agent? Which can undergo reduction itself and can oxidize others. So fluorine is the strongest oxidizing halogen. Okay, now see, if we see these reactions, just like here, fluorine, when it reacts with any other halide, then it will form fluoride and the other halogen will be given out. So a particular halogen can act as oxidizing agent for some higher halogen, just like our order is fluorine, chlorine, bromine, iodine. So fluorine will be oxidizing agent for all other three. Chlorine will be oxidizing agent for bromine and iodine. Okay, similarly bromine will be oxidizing agent for iodine. So this way it goes. Okay, now reaction with metals and non-metals. Halogens react with metals to form metal halides. So there is formation of metal halides, just like magnesium reacts with bromine, then it forms magnesium bromide. Now if we talk about their ionic nature, then what we feel, now see, in this case there is bond of M means metal and Br is bromo group. So this is the bond in this case. Okay, now ionic character depends on this thing. The order is that fluorides will be having maximum ionic character and iodides will be having a minimum ionic character. Why is it so? Because F or F negative ion that have maximum electronegativity, because of maximum electronegativity of fluorine, F negative ion is strongly formed. Okay, so development of charges is maximum in case of fluorides. So what happens? That becomes most ionic. And in case of iodine, it is having least electronegative nature. So what happens? There is minimum ionic character. Okay, now reaction with hydrogen. Now when these halogens, they react with hydrogen, they form hydrogen halides. What do we say? Hydrogen halides. They are represented with general formula HX. Okay, now see, since they can produce H positive ions, so all hydrogen halides, they are acidic in nature. So there are all properties of this hydrogen halide. They are acidic in nature. They will show reducing agent character because they can release H positive ion, or they can get any other substance added with hydrogen. So they will also show reducing agent character. Then their stability, that will keep on decreasing as we move from top to bottom. Okay, so this way all properties will be shown by hydrides of halogen. So in general what we say, it is HX, like HF, HCl, HBr, HI. Okay, now reactivity towards oxygen. Halogens, they form many oxides with oxygen, but most of them are unstable. Now see, two oxides are there. Fluorine forms two oxides, OF2 and O2F2. Now see, here we have said that fluorine forms two oxides. This is just, we are saying that the compound formed by fluorine after combination with oxygen. But otherwise what we have to say, we have to say these are the fluorides of oxygen. We have to say these are fluorides of oxygen, not oxides of fluorine. Okay, here what we are saying, here we just want to say that there is formation of compound after combination with oxygen. Okay, now why do we say oxygen fluorides? Because fluorine is more electronegative than oxygen, so it is fluoride of oxygen, not oxide of fluorine. Okay, now chlorine, bromine, iodine, they form oxides in which the oxidation states of these halogens range from +7 to +1 to +7. Now just now we discussed how this can happen because of availability of vacant d orbital. So because of that, electrons jumps to higher orbits and then they form different oxidation states. They will range from +7 to +1 to +7. Okay. Now stability of oxides. Stability of oxides will be like this. I is greater than Cl is greater than Br. The higher oxides of halogens tend to be more stable than the lower ones. Okay, so this is because of these two theories, the combined effect of kinetic and thermodynamic factors. Okay, because of two different factors, the overall effect we have to see, and that effect is that higher oxides, they are more stable and lower oxides are less stable. Okay, now see, chlorine also forms oxides like Cl2O, ClO2, Cl2O6, Cl2O7, and these are highly reactive oxidizing agents. Okay, they tend to explode. ClO2 is a bleaching agent. So this is a bleaching agent. Where it is used? In paper industry it is used, in textile industry it is used, and since it is a bleaching agent, so for treatment of water also it is used. Okay, so these are the oxides of chlorine. Now oxides of bromine. Bromine oxides are like Br2O, BrO2, BrO3, but they are having less stability. Okay, they are having less stability, and they exist only at the low temperature. Okay, they are very powerful oxidizing agent. Now see, since they are less stable, so they can act as powerful oxidizing agent. They can release oxygen and that can be added to any other, so they can behave as powerful oxidizing agents. Okay, similarly iodine oxides, iodine also forms I2O4, I2O5, I2O7. Such oxides are formed, and how they are, their behavior is, they are insoluble solids and they decompose on heating. I2O5 is very good oxidizing agent and is used in the estimation of carbon monoxide. Now see, in 11th standard you have done qualitative and quantitative analysis where we check the presence of elements. Okay, so in estimation of carbon monoxide also I2O5 is used. Okay, now how halogens react with other halogen, how one halogen can react with any other halogen. So this we are going to discuss in this session itself, that such compounds where all the atoms are different halogens, they are called interhalogens. Okay, so what we will say, that halogens react among themselves also to form certain molecules, and those molecules are called interhalogens. Now fluorine is the first element, so it will show some properties which are different from other members, and that will be termed as its anomalous behavior. Now see, ionization enthalpy, electronegativity and electrode potentials, they are all higher for fluorine than expected. Okay, so whatever we expect, these all values are higher for fluorine. Ionic and covalent radii, melting point and boiling point, enthalpy of bond dissociation and electron gain enthalpy are quite lower than expected. Okay, now this is because of the reason that it is having very small size, and because of that electron density value is very high. So because of that there is inter-electronic repulsive forces existence. So because of that thing, these all things are happening. Okay, so anomalous behavior of fluorine is due to its small size, highest electronegativity, low fluorine-fluorine bond dissociation enthalpy, and non-availability of d orbital. Most of the reactions of fluorine are exothermic. Exothermic, you know, where there is release of energy. Okay, so it forms only one oxoacid, while other halogens form number of oxoacids. Oxoacids, you know, the compounds formed by the combination of oxygen, hydrogen and the element for which we are talking about oxoacid. Now here we are talking about fluorine, so fluorine forms only one oxyacid, and others, they form a large number of oxoacids. Hydrogen fluoride is a liquid due to strong hydrogen bonding. Other hydrogen halides are gases. So when we discussed the formation of hydrides, then there was formation of HF, HCl, HBr, HI. So out of these all, HF is a liquid and others are gases. Why? Because of strong intermolecular hydrogen bonding. Now let us come to important element, that is chlorine. Chlorine was discovered in 1774 by Scheele by reaction of hydrochloric acid on MnO2. In 1810, Davy established its elementary nature and suggested the name chlorine on account of its color. So its color is greenish yellow, and in Greek chloros means greenish yellow color. So on the basis of that, Davy gave the name of chlorine. Okay, now how it can be prepared? Now see, either we heat manganese dioxide with concentrated HCl, then we can get this, or we can take potassium permanganate and we treat it with HCl, then also we can get chlorine. So what we have to do, we have to take hydrochloric acid and either we can add manganese dioxide or we can add potassium permanganate. So in both the cases there will be formation of chlorine gas. Okay. Now on large scale, how can we produce chlorine? There are two processes. One is Deacon process. In this what we do, oxidation of hydrogen chloride gas is done by the atmospheric oxygen in the presence of CuCl2. So CuCl2 acts as catalyst and HCl reacts with oxygen and it undergoes oxidation. Because of that, what happens? Chlorine, Cl2 gas is liberated and H2O is formed. Okay. So in electrolysis process, what we do, we take brine solution. What is the brine solution? It is the concentrated sodium chloride solution. So concentrated sodium chloride solution is taken as electrolyte and we do the process of electrolysis. What happens? Cl negative chlorine chloride ion moves towards anode and there is oxidation and there is formation of chlorine gas. Okay. Now if we talk about other chemical reactions, then chlorine is a byproduct of so many other reactions also. Okay. Now see, this diagram shows the process of electrolysis. Okay. What is electrolysis? It is the process of conversion of electrical energy into chemical energy. Okay. So whenever electrical energy is provided, then there is some chemical change. That process is called electrolysis. Okay. Now what are the properties of chlorine? Now see, just now we said that it's a greenish yellow gas, it has pungent smell, it has suffocating odor, and it is 2 to 5 times heavier than air. Okay. Now it can be liquefied easily into greenish yellow liquid which boils at 239 Kelvin. So it is soluble in water. Chlorine reacts with a number of metals and non-metals to form chlorides. Now see, these are the metals: aluminium, sodium, iron, and these are non-metals: phosphorus, sulfur. So it can react with non-metals also and metals also. And what is it is going to form? It is going to form their chlorides. Okay. It has great affinity for hydrogen. So it can combine with hydrogen very easily and it reacts with compounds containing hydrogen to form HCl. Now see, just like if it combines with hydrogen, then there is formation of hydrochloric acid. Okay. So it has great affinity. It can combine easily with hydrogen. Now see, if we take hydrogen sulfide gas and chlorine is made to react with this, then there is formation of hydrochloric acid. Similarly, if this hydrocarbon is taken, okay, then there is formation of HCl and carbon goes out. Okay. With excess of ammonia, chlorine gives nitrogen and ammonium chloride, whereas with excess chlorine, nitrogen trichloride is formed. Okay. Now see what we are saying. We are saying that if we take ammonia in excess, Okay, then nitrogen gas is formed along with ammonium chloride, and if we take chlorine in excess, then this explosive is formed. NCl3 is an explosive. Now see why we are saying that there is excess of ammonia in first case, because we have taken chlorine as 3 moles and we have taken ammonia equal to 8 moles, and in the second case we have taken chlorine equal to 3 mole, but we have taken ammonia as 1 mole only. Okay, so in the second case chlorine is in excess, and in the first case ammonia is in excess. Okay, now with cold and dilute alkalis, chlorine produces a mixture of chloride and hypochlorite, but with hot and concentrated alkalis it gives chloride and chloride. So see, chloride is always formed, but if it is dilute alkali then hypochlorite is formed, and if it is concentrated alkali then chlorate is formed. Okay, so if we take cold and dilute sodium hydroxide, then sodium hypochlorite is formed. Okay, and if we take hot and concentrated, then sodium chlorate is formed. Okay, with the dry slaked lime it gives bleaching powder. Okay, with dry slaked lime it gives bleaching powder. Now see, this is the bleaching powder. Okay, now here there is some problem in that. It is, the formula is CaOCl2. This is bleaching powder formula, so we don't have to put bracket over here. This bracket will not be there, and the formula will be CaOCl2. Okay, this is bleaching powder. So CaOH whole twice plus Cl2, it gives CaOCl2 plus CaCl2 plus 2H2O. Okay, now it oxidizes ferrous to ferric. Okay, now see, ferrous sulfate changes to ferric sulfate. Okay, by the action of chlorine. Okay, sulfite changes to sulfate, sulfur dioxide changes to sulfuric acid, iodine changes to iodic acid. Okay, so what we have to do in case of iron sulfate, we have to take it in acidic medium, and in all other cases we have to take aqueous chlorine. Okay, okay, now chlorine reacts with hydrocarbons and gives substitution products with saturated hydrocarbons and addition products with unsaturated hydrocarbons. For example, see, this is saturated hydrocarbon and this is unsaturated hydrocarbon. Okay, so with saturated hydrocarbon it has formed CH3Cl, and with unsaturated hydrocarbon it has formed dihalide. Okay, so here it forms monohalide and here it forms dihalide. Okay, now see this reaction which we have done, this one, in this reaction there is formation of a large number of halides. Okay, so we cannot say that it only produces monohalide, it can give a large number of halides. They may be dihalide, trihalide or tetrahalide also. Okay, so what we are saying here, that in this case there is substitution. Substitution means H is replaced by Cl. Okay, and in unsaturated cases there is addition. Addition means where unsaturation is there, that bond will break and there will be addition of the halogen. Okay, just like here in this case there is C double bond C. So what happens, C single bond C comes out to be there as a product, and that is associated with chlorine atoms. Okay, okay, now see where we can use chlorine. Okay, now see, it is used for bleaching wood pulp. Okay, it is a very good bleaching agent in paper industry and in clothing industry, textile industry also it is used. In the extraction of gold and platinum also there is use of chlorine. In the manufacture of dyes, drugs and organic compounds there is use of chlorine. in sterilizing drinking water. Okay, in order to kill all the bacteria we can use chlorine also. Okay, and some poisonous gases are also produced by the action of chlorine, just like phosgene or tear gas or mustard gas. Okay, so these are all poisonous gases which can be produced by the action of chlorine. Okay, now let us discuss second important compound. It is hydrochloric acid. So Glauber prepared this acid in 1648 by heating common salt with concentrated sulfuric acid. Davy in 1810 showed that it is a compound of hydrogen and chlorine. So how it is prepared? For preparing it in laboratory, it is prepared by heating sodium chloride with concentrated sulfuric acid. So concentrated sulfuric acid and sodium chloride, they are mixed and heated. Okay, then there is formation of HCl. Now this sodium hydrogen sulfate, this can again combine with sodium chloride to form sodium sulfate and HCl. Okay, so this is the simple method to prepare hydrochloric acid. Now what about its properties? It is a colorless and pungent smelling gas. It is easily liquefied to a colorless liquid and freezes to a white crystalline solid. It is extremely soluble in water and ionizes as below. Okay, now see how it ionizes. This is our acid. When we take its aqueous solution, then there is formation of H3O positive. It is hydronium ion, H3O positive. Okay, now see, positive sign is here, so it is H3O positive and Cl negative. Okay, now it reacts with ammonia and gives white fumes of ammonium chloride. Now see, when ammonia and hydrochloric acid they come in contact, then there is formation of white fumes. Those fumes are of ammonium chloride. Okay, so this test is also used to check the presence of ammonia. Okay, this is important test. Now when we take 3 parts of concentrated HCl and 1 part of concentrated nitric acid, then that mixture is known as aqua regia, and that mixture is highly reactive. Okay, it can dissolve even noble metals just like gold, platinum or silver. So now see what is there. It is combination of acids. So acidic thing is there. There is nitric acid and there is hydrochloric acid. So chloride ion is there, nitrate ion is there, and H positive ions are there. So whenever these things combine, either silver or this gold or platinum, then they get dissolved to form their salts. The salt is chloride salt. Okay, now this whatever is formed, this is a coordination compound. There is formation of a complex. Okay, now hydrochloric acid decomposes salts of weaker acids. For example, carbonates, hydrogen carbonates, sulfites, etc. Now see, what do we mean by this? We mean to say that if there is presence of carbonate or hydrogen carbonate ion, then acids can produce carbon dioxide gas from that. Okay, if there is sulfite ion, then sulfur dioxide gas can be produced by the action of acid. Okay, now what are the uses of hydrochloric acid? It is used in the manufacture of chlorine, ammonium chloride and glucose. Okay, it is used for extracting glue from bones and purifying bone black. Okay, for purification of bone black also it is used. In medicines also it is used, and it is a very important laboratory reagent. Okay, now we come to important thing. This is interhalogens. Just now we discussed these are the compounds formed by the combination of halogens. Okay, so when two different halogens react with each other, interhalogen compounds are formed. They can be assigned general compositions as XX dash, XX3 dash, XX5 dash, XX7 dash. Okay, so whatever is in less amount, that will be large sized halogen, and whatever is in small amount, that will be, whatever is in more amount, that will be the smaller sized halogen. Okay, just like if we say it is IF7 or IF5, then I is in less amount, so this is having higher size, larger size. F is having more in number, this is more in number, so it will have small size. Okay, so these are interhalogens. Now how can we prepare interhalogens? Now this is very simple. Whatever we have to prepare, whatever halogens are there, we have to just take those halogens, but temperature and pressure should be known to us. Okay, at a particular temperature they will form that particular combination. Just like if we have to prepare CLF, then temperature should be 437 Kelvin. But if we have to prepare ClF3, then temperature should be 573 Kelvin, though reactants are same. Okay, so this is what is to be kept in mind. Similarly, ICl or ICl3 can be prepared, BrF3 can be prepared, and BrF5 can be prepared. Okay, so in what ratio we are mixing the reactants, that also decides the formation of product. Okay, now what are the different properties of interhalogens? These are all covalent molecules and are dimagnetic in nature. Okay, so first thing is they are all covalent molecules, there is no ion formation, and they are dimagnetic in nature. They are volatile solids or liquids except CLF. CLF is a gas. Okay, their physical properties are intermediate between those of constituent halogens, except that their melting point and boiling points are a little higher than expected. Okay, so their melting point and boiling point values are more than expected because of their extra stability. Okay, their chemical reactions can be compared with the individual halogens. Okay, we want to compare that how they are going to react, then whatever properties are shown by halogens, we can compare many properties, will be like that only. Okay, in general, interhalogen compounds are more reactive than halogens. So interhalogen compounds are more reactive than halogens. Why? Because they are heteroatomic. In case of halogens, they are homoatomic. Fluorine is the most reactive that is there, that is exceptional case. But if we compare interhalogen, just like ICl and Cl2, then ICl will be more reactive than this Cl2. Okay, this is because when we take two different halogens, then the bond between them is weaker. Okay, but when we take same halogens, then the bond is slightly stronger. Okay, fluorine is the exceptional case, for that we are not talking. All these undergo hydrolysis, giving halide ion derived from the smaller halogen and a hypohalite. Okay, so what happens when interhalogens are treated with water? There is formation of halogen acid and a hypohalite, HOX. It is hypohalite compound which is called hypohalite. Okay, now let us discuss structures of these interhalogens. Just like here, it is ClF3. Now see, when we talk about ClF3, Cl as well as F, they all have 7 electrons in their valence shell, but Cl is central atom over here. So this central atom is having 7 electrons. How they are arranged? Their 3 electrons are making bonds with fluorine atoms. 3 are making bonds with fluorine atoms, and 4 electrons, those 4 electrons are there in 2 different orbitals. Okay, so this way its geometry becomes T-shaped. Okay, in case of IF7, I is in the center and it is bonded to 7 fluorine atoms, and all of its electrons are used in that. So 5 of the bonds are in the same plane, forming a pentagon, and one is above the pentagon and one is below the pentagon. So its geometry is called pentagonal bipyramidal geometry. So what are the uses of interhalogens? These compounds can be used as non-aqueous solvents. Interhalogen compounds are very useful fluorinating agents. Okay, if you want to add fluorine, then they will act as a very good fluorinating agent. ClF3 and BrF3 are used for the production of UF3 in the enrichment of uranium. Okay, so these are the different uses. Now next is oxyacids of halogens, oxyacid or oxoacids. Now see, due to high electronegativity and small size, fluorine forms only one oxoacid. Fluorine will form only one oxoacid, and others they will form different oxoacids. Okay, so why fluorine forms only one? Because of its small size and because of its high electronegativity. Okay, now they are stable only in aqueous solutions or in the form of their salts. So see, if we want to isolate these in their pure state, then it is difficult. They are stable in their aqueous solutions or in the form of their salts. Now see, different categories you can say. Hypohalous acids. How we represent these? As HOX. This is hypohalous acid. Now if there is Cl in place of X, then we will say hypochlorous acid. If Br, hypobromous acid. If iodine, then hypoiodous acid. Okay. Now second category is halic acid or halous acid. So this is in the category of HClO3. Only chlorine forms this. Then halic acid. Halic acid means where the oxidation state is 5. So it is HClO3. If I talk about chlorine, then HClO3. Similarly, halic acid with 7 oxidation state, this forms HClO5. So what all we discussed? We discussed that there are these categories of oxoacids, just like HClO, HClO2, HClO3, HClO4. Okay, so these are the categories, 4 different categories. Now what we can see over here, we can see here oxidation state as +1, +3, +5, +7. Okay, so these were the different oxidation states. Now let us discuss the structures of oxyacids. Now see, HClO, it is like this. H will be bonded with O only. Why? Because only then it can be given out as H positive ion. If it is not bonded with O, then it cannot be given out as H positive, and that compound will not show its acidic character. Okay, so hypochlorous acid, this is chlorous acid, this is chloric acid, and this is perchloric acid. Now see, if we compare their acidic character, then all of the 4 will release H positive ion. Okay, now when they release H positive ion, then what different ions they will be forming? HClO will form ClO negative, HClO2 will form ClO2 negative, HClO3 will form ClO3 negative, HClO4 will form ClO4 negative, and when we see their structure, then it will have one resonating structure, this will have 2 resonating structures, this will have 3, and this will have 4 resonating structures. So what happens now? That ion which is having maximum number of resonating structures, that will be most stable. So it means that if we want to compare the acidic character, then this compound will form this ion most easily after losing H positive ion. Okay, so this will have maximum acidic character. And HClO, if we talk about, then this will form a ClO negative ion after losing H positive ion, but it will be the least stable. So it will have minimum acidic character. Okay, so what is the acidic character among these oxyacids of chlorine? HClO4 is greater than HClO3 is greater than HClO2 is greater than HClO. Okay. Okay. Now, whatever we have discussed, on the basis of that, you have to solve these home assignments. Okay. Thank you.